Hello and welcome to the lecture in stats on central tendency, variability, skew, and kurtosis. We are going to start with central tendency. So central tendency is going to be our first main descriptive statistic we're going to look at. We've looked at frequencies, so technically that's descriptive statistics, but really when it comes down to it for statistics, we are interested in a few different things, and one of them is a measure of central tendency. So central tendency is a descriptive statistic that basically helps us summarize or describe our data. And what it is doing is it's describing the most typical or representative value in the data set. So it's going to be central tendency is one value, and it is our value that is the one value that is either most typical, most average, most representative of the data set as a whole. There are three main measures: the mode, the median, and the mean. We are not going to talk about the mode much after right now. Just note that we use the mode when we're dealing with categorical variables, and not when we're dealing with frequencies, but when we're dealing with comparing categorical variables. So in this case, we're not going to look at it beyond this. You should already know what the mode is, that the mode is the most frequent item. So if you have frequencies, it's the one that is the most frequent. Before we get into actually talking about the mean, median, and mode, and sorry, just a correction from the previous slide, but we'll talk about the mode just a slight bit more, but not much. But before we really get into talking about the mean and the median, let's talk about something that affects statistics, and that is outliers. So outlier is going to be any score that is very extreme relative to the majority of the scores in the data set. So for example here, we have these values here. We've got 1 through 5, and then this 82 in there. And basically, when we're dealing with outliers, we have to feel that there's something wrong or unexplained about that score. And with this, the number 82 is considerably larger than any of the others. It stands out. If we were doing like 1 through 75 and then had an 82, that 82 isn't really that big of a difference from the others if you have a 75, 70, stuff like that. But this 82 here is very different than the others. And what's going on here is it's most likely either a data entry error or an anomaly in the data. And data entry errors are more common than you think. Let's say this is a variable that can be rated on a 1 through 5. So if it's 1 through 5, 82 is impossible. It's likely that someone was putting in a 2 and accidentally hit the 8 and then the 2. So data entry errors is common for this. It's why whenever you're running statistics on data, one of the first things you should do is check for outliers, order them from lowest to highest, or do a frequency distribution. That's a good thing to do, or good reason for frequency distributions, is you do a frequency distribution. And if you did a frequency distribution on this, you'd see that the 1, 2s, 3s, 4s, even the 5, those are occurring. Well, the 5 is only once as well, but then you've got this 82 that's once. So again, frequency distributions can help you identify outliers. Why am I talking about outliers though? Because outliers are going to, if you decide to keep them in, if for some reason it's not a data entry error, if it's an anomaly in the data that you're still interested in, then it's actually going to affect what measure you use as central tendency. Because this first one we're going to talk about in just a minute, the mean, is actually susceptible to outliers. Outliers is going to change the mean sometimes drastically. Let's get into the mean. This should be stuff you already know. That the arithmetic mean, the average, it's the sum of all scores divided by n. So x1 plus x2 plus x3 all the way on divided by n. Example here, just price of gas over 6-week period. it was calculated here. Each week's gas prices were calculated, and then looking at, well, what is the average weekly gas price? Add all those together, divide by 6, and you get a mean of 42.89. If you haven't seen it before, this is the symbol we're going to use for mean, a bar over something. So x bar would be the mean of x. Y bar would be the mean of y. Any other variable, any other thing where we put the bar over the top of it, we're basically talking about the mean of that variable. Median, on the other hand, isn't the average of scores, it's the centermost score. So it's going to be the score that basically divides the distribution in half. It's going to be the score that's in the center of all of the scores, irrespective of the actual value of the scores, as long as they're in order. One thing that's always of note with median, I shouldn't have to tell you guys, I'm expecting you already know this, but with the median, you have to put the data, the numbers, in order from lowest to highest before you can find the median's location. So if you have a set of scores and they're not set from lowest to highest, you can't get the center one. If you have to put them from lowest to highest first. There's two different ways to get the median, or there's one rule that's split into two for how to get the median. If you have an odd number of scores, so like in our example here, there's 5 scores, the median is going to be the centermost. So you just cut off the ends and you're left with the centermost score. Another way to do it with an odd number of scores is if you take, so that's easy to do with 5 scores, but if you've got more than that, it becomes more difficult. So one thing you can do is take and do n plus 1, so our n here is 5, but n plus 1 divided by 2, and that is the number of the score. Let's look at that a little bit more. Here we've got n, we've got 5, so 5 plus 1 is 6. 6 divided by 2 is going to be equal 3, so the third score. This is the first score, this is the second score, this is the third score. 1, 2, 3. So again, our median is that third score. So n plus 1 divided by 2, that actually works for the next one as well, but if you have an even number of scores, it's going to be the average of the 2 centermost scores. So let's use that n plus 1 divided by 2 there. We've got 1, 2, 3, 4, 5, 6 scores. So 6 plus 1 divided by 2. So we've got 7 divided by 2 equals 3.5. So it's going to be halfway between the third score and the fourth score. So we've got 1, 2, 3, 4. It's going to be halfway between these two. And to get halfway between the two, you just take the average of them. So in this case, we have 17 plus 21 divided by 2, and we get 19. So our median here is 19. And again, easy way to do it, odd number of scores, it's the centermost score. Even number of scores, it's halfway between the 2 centermost scores. Or another way to do it is n plus 1 divided by 2 and count that many from the beginning, and that's what you get. But going back, you have to put the values in order. Okay, I am contradicting myself from earlier where I said I wouldn't talk about the mode anymore, but I do want to talk about it just very briefly, and just that, again, the mode is the most frequently occurring score, and there is 3 different types of modes you can have. Unimodal, where there's 1 mode, bimodal, where there's 2 modes, or multimodal, where there's 3 or more. You can also have no mode. Some people say multimodal and no mode are the same thing, meaning that if, let's say, every value in the distribution only has 1 occurrence, 1 frequency, some people will call that no mode, some people will call it multimodal, and every value is the mode. it's subjective, it's dependent, and that's one of the things actually I'm going to talk about real quick briefly here, spending more time on the mode slide than and after I said I wasn't even going to talk about it. One of the things in statistics is that there is a lot of different methods for statistics. There's a lot of different ways to do stats. There's a lot of different people who use different terms to mean the same thing, and some people even use the same terms to mean different things. So it's one of those things when you're looking at it and when you're Googling this and stuff like that, that can get complicated is the fact that, like this example here, where some people will say if all of values have in a distribution have one frequency, that there's no mode, and others will say it's multimodal and all of them are a mode. There is no definitive correct way to do it. It's more of find the way that works for you, and if you're taking more stats classes, find the way that the professor of that stats class is looking for, because some professors, I said in my introduction, I've taken 14 stats classes. Some stats professors are really picky, and some stats professors are not. I'm generally not picky. If I understand what you're getting at, then we're all good. Okay, now we're going back to the mean real quick, talking about some important properties of the mean. And this is good to know information. So the mean is sensitive to the exact value of all scores in the distribution. This is why that outlier it can affect it. So the mean is sensitive to those extreme scores because it's sensitive to every value in the distribution. If one value in the distribution changes, your mean is going to change. The mean is in a sense going to be our balance point, not our centermost point, our balance point. So we have, let's say we've got a 1, a 2, and a 10. Our mean is going to be pulled towards this 10 and is going to be the balance point on the distribution. And in this case, the mean would actually be closer to over, let me erase that, because by balance point it's going to be closer to these. It's going to be somewhere over there, somewhere around 3.5. Something we're going to talk about in just a minute, but when we're talking about variability around the mean, the sum of the deviations about the mean is equal to 0. So let's look at these values. Let's just do 1, 2, and 3. So if we had an x of 1, 2, and 3, here our mean would be equal to 2. Another way to calculate that would be 1 plus 2 plus 3, which is 6, divided by our n, which is 3. Our n is 3, so we'd get 2. But if we took each value and subtracted it from the mean, so 1 minus 2 is -1, 2 minus 2 is 0, 3 minus 2 is 1, and added those together. So we've got the sum of the deviations about the mean. You add -1 to 0 to 1, you get 0. So the sum of the deviations about the mean is always going to equal 0. This is relevant and important because when we do variability, we want to know how spread out the scores are. We cannot do just the sum of the deviation from the mean, because if we just do the sum of the deviations from the mean, we're always going to get this 0. What we do instead is what's called the sum of the squared deviations from the mean. And we do this in a sense because we are now interested in how much deviation there is from the mean, but in a way to eliminate the 0 of the sum of them, we square each one. So now we've taken each of these values from the mean, running out of room up here, and we square each of them. So now we're taking the x minus the mean, but we're squaring it. So we've got this -1. When we square it, it becomes 1. 0 squared is 0, 1 squared is 1. We get 2. So our sum of the squared deviations from the mean is equal to 2. And we will come back to this because this is one of the things we will do to get measures of variability, because this is what's called the least squares criterion, meaning the smallest way to get variability. Last thing just to talk about is over repeated samples. So if I collect a group of 10, then a group of 10, then a group of 10, the mean is actually less subject to sampling distribution, or sorry, sampling variation, less subject to sampling variation than other measures of central tendency. What I mean there is you're going to get less variability in your mean over multiple samples than you would with your median. Outliers can mess with that, but in general, over multiple samples, you're going to start to account for outliers, and then you'll have less variability. Whereas the median, which we'll get to next, over multiple samples, you can have more variability because it's only subject to that middle score. So the median is less sensitive than the mean to extreme scores. That should be pretty self-evident. But the median is more subject to sampling variability. But what I mean here is if you've got scores 1, 2, 3, 4, and 5, the median, the middlemost number, is 3. If you've got scores 1, 2, 3, 4, and 1 million, your median is still 3. So extreme scores do not affect the median. However, over multiple different samples, you're more likely to get this 3 to change one way or the other due to sampling variability. So let's tie this back to what we talked about in the first set of slides, which is levels of measurement. Well, now we're going to talk about what measure of central tendency is important for what level of measurement. So for nominal variables, just names, mode, because you're just looking at frequency, that's all that's important. For ordinal variables, you should use the median. That's because to use the mean, distance between the values is important, but the median, that's just looking at the centralmost score. Difference between 1 and 2 and 2 and 3 doesn't matter when you're just looking for the centralmost score. But for interval and ratio, we use the mean. Unless, my marker just fell apart. Sorry, I got to get this working again so I can write again. Unless outliers are present. And what I mean by unless outliers are present, unless outliers kept in your data. If you didn't find a way to get rid of your outliers, you're not supposed to use the mean, you're instead supposed to use the median. Let's just add a few things, not too much, but central tendency and symmetry. This is symmetry of your distribution. So a symmetrical distribution looks like so. I'm not a perfect artist, but symmetry just basically means that the right side matches the left side. It's the same, it's a mirror of the left side. Actually, it looks like a little bit like a duck there. Huh. I am not an artist. I am not even anywhere near an artist. You'll find that out as I'm drawing things throughout the semester. And it's amazing that I even had something that even looked a little bit like a duck there. But no, symmetry just basically means that the left side and the right side they look alike. They are symmetrical between the two. And when you're dealing with the mean, the median, the mode, if you've got a unimodal distribution and they're perfectly symmetrical, that is the left side looks exactly like the right side, then in that case the mean, the median, and mode are equal. However, if your distribution is skewed to one way or another, which we'll talk about, which we'll look at in just a little bit, looking at these skewed distributions, then your median is going to tend to be more towards where this is, whereas the skewness, so median is up here, your mean is going to be pulled towards the tail in a skewed distribution. So the mean and median will not be equal in a skewed distribution. So to summarize central tendency before we get into variability, you have just this handy chart where it talks about uses for the mean, median, and mode, the formula for them, the advantages and disadvantages. This is summarizing everything else. I don't need to cover this. You can go back and look at it on your own though. Next, we're going to talk about variability, and then we'll finish up by talking about skew and kurtosis. So let's start with variability. Variability is, in a sense, dispersion. Variability is a spread of scores around a central location. This is a couple different ways where we can look at variability. So in these two distributions here, in both of them, we have a mean of 15. So our centralmost score is 15. And really, this is going to show why it's important to have a measure of dispersion as well. If you just have a mean of 15, you just have your measure of central tendency. You don't have anything else. What you're going to do in these two separate distributions, in these two separate data sets, you're going to say that they're basically equal because they both have means of 15. However, when you look at how they're graphed out, you can look and see that even though they have the same mean, the spread of scores is very different between the two. In the second one, the scores are more spread out there, way more spread out around the mean. So this is why we need a measure of variability. The measure of central tendency tells us a lot of information, but just like when we're talking about the difference between a frequency and a relative frequency, you run into the challenges of it doesn't give us enough information to make comparisons. So we've got two different data sets here, both with the same measure of central tendency. We can't compare them though because we don't have a measure of dispersion. Once we throw a measure of dispersion on though, we can compare them. And a good way to look at this is if you scored an 18 on each of these, which distribution would your relative standing be higher? Well, in this one, it looks like you're ahead of about 66%. About. In this one, it looks like you're ahead of about 95%. So the answer is in distribution 1, your relative standing is higher with a score of 18. That's because the less dispersion there is, the higher you'll be relative to the distribution on any score above the mean. And any score below the mean, the lower you'll be in relative to the rest of the distribution. Any fixed value, that is, with a distribution that has less dispersion or less variability. So there are two types of variability we're going to look at. We'll get to that in just a second. Before that, so what does measures of dispersion do? They describe the differences between people in the data set. They measure the degree to which scores are spread around that measure of central tendency. This is that one I keep coming back to. So they are measuring the spread around, and as I've said a few times, you need both a measure of central tendency and a measure of dispersion or variability to interpret the meaning of any individual score. If, again, going back to that previous one, if you have a mean of 15 and you get a score of 18, what does that mean? All you can say at that point is you scored above the mean. You cannot say how well you scored above the mean, what percentile you are, any of that. To get that, you need your measure of dispersion or variability. I got ahead of myself, but now we're back to that. The two types of variability that we're going to look at are range and interquartile range and standard deviation of variance. Range and interquartile range go with the median. Standard deviation of variance go with the mean. I actually have this on a slide coming up, but I'll just put that there for now. So these are the two types of variability, and again, they each associate with our main measures of central tendency. Let's start with range. So we're now looking at our measure of variability around the median. The range, pretty easy. It's going to be the highest score minus the lowest score. So even easier to calculate than the median. You don't even need to put them in order, you just need to find the highest and the lowest score. putting them in order can help you find those, but you don't need to, just find the highest and the lowest. So if we got hours spent studying in a week amongst 1, 2, 3, 4, 5, 6, 7, 8, 9 students, the range is going to be anywhere from the lowest 2 to the highest 18. So you take the highest minus the lowest, 18 minus 2, you get our range of 16. Range is easy. The next thing we'll talk about is a little bit more complicated, because range, just take the highest minus the lowest. Now we're going to start talking about something else, which is called quartiles. Quartiles are things that split distributions, and they split distributions into equal quantities. So they're going to be quartiles. Another way to do is the 25th percentile is the first quartile, the 50th percentile is the second quartile, and the 75th percentile is the third quartile. Now you should already be catching on to something here. Let's see if I can write without being too messy. So you should already catch on to something, and that is, what is the second quartile? You already know what the second quartile is. The second quartile is also the median. It is the thing in the value in the center of the distribution that splits the distribution in half. The quartile 1 and quartile 3 are also going to be splits, but instead it's going to split quartile 1 is going to split everything from the lowest value in the distribution to the quartile 2, and quartile 3 is going to split everything from quartile 2, the median, and the highest value in the distribution. So these are also splits in much the same way as the median, and on the next set of slides I'll show you the formula on how to calculate that, because there's a little bit more going on there, but I'll get to that in 2 slides. Before I get to that, I need to talk about the interquartile range, because the interquartile range, and when we get to it, the semi-interquartile range, are the 2 measures of variability that we use for the median. Specifically, we use the median and the semi-interquartile range together as our measure of central tendency and variability. So when we get stuff like the interquartile range, which we're factoring in now, all that is an intermediate step to get to the semi-interquartile range. So the interquartile range, it's going to be the difference between the 75th percentile, the third quartile, and the 25th percentile, the first quartile. So all it's going to be is the middle 50% of scores. So just like the median cuts off all of the scores outside of that centralmost score, the interquartile range cuts out all scores outside of the middle 50% of scores. And to get the semi-interquartile range, you just take that and divide by 2. Let me give an example here, and we'll talk about the formula on how to actually figure out what the first quartile is and the third quartile, because just like when we figured out the second quartile, if you remember, quartile 2 was n plus 1 divided by 2, or another way to do that would be n plus 1 times 0.5, because it's the 50th percentile. You can do that exact same thing to get the first and the third quartile. So to get the first quartile, again, let's just real quick before we do that, let's calculate this median again. So our n here is 19. We put the values in order. So for semi-interquartile range, and to get to it, we need to, for interquartile range and semi-interquartile range, just like median, you need to put the values in order. So to find quartile 2, which is also the median, you take n plus 1 and divide by 2, or n plus 1 times 0.5. It's another way to do it, because the second quartile is the 50th percentile. So if we take n plus 1, we get 19 plus 1, we have 20, times 0.5, we get the 10th value. So the quartile 2, the median is not 10, it's the 10th score. So we start up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10th score. We get our quartile 2, we have our median. That is, again, back how you'd calculate the median. Well, you can calculate the first quartile in a very similar way, and that is, it's going to be n plus 1 times 0.25, because again, the first quartile is the 25th percentile. So in this case, we did n plus 1, 19 plus 1, times 0.25, that's 20 times 0.25, we get a score of 5. And it isn't the quartile 1 isn't 5. Don't make that mistake. Some students do make that mistake. The first quartile is the 5th value. In this case, it just happens to be the 5th value is 5. For quartile 3, similar thing, except now we're looking for the 75th percentile, so it's 19 plus 1 times 0.75. We get the 15th score. And the 15th score here is 14. And that's where we get that 14 for the third quartile. So quartile 3 is 14, quartile 1 is 5, quartile 2 is 8. And then the last thing to do is calculate the semi-interquartile range. That is, you just take quartile 3, 14, minus quartile 1, which is 5, divide by 2, and you get 4.5. So our SIR is equal to 4.5. And our median is equal to 8. And that is our measure of central tendency and dispersion for the median. Next thing I want to talk about is variance and standard deviation. Now, when we're getting into variance and standard deviation, this is what we will do most of the semester. So I've mentioned briefly before about parametric and non-parametric statistics. So what is the big difference between parametric and non-parametric statistics? Parametric statistics uses the mean in the standard deviation. Non-parametrics uses the median in the semi-interquartile range. The vast majority of statistics that's out there is parametric, so we're going to use the mean. Actually, everything we're going to do in here except one lecture is going to be parametric. So for the most part, this is what we will be doing the rest of the semester, other than when we're talking about the 1 week on non-parametric and probability. So variance, it's a descriptive statistic used to summarize how scores vary in the data set. The variance and the standard deviation are used with the mean, and specifically we use the standard deviation. So much like the interquartile range got us to the semi-interquartile range, the variance gets us to the standard deviation. But you should not use these when the mean is not appropriate for use, such as nominal or ordinal data, or when you've got extreme outliers that are messing with your data. Let's get into calculating variance and standard deviation. So as we already said when we were talking about the mean and we looked at how we took scores from the mean, it's actually impossible to calculate an average deviation score. If you remember, just like we used in our example earlier, if you had the sum of x minus the mean, it is always going to equal 0. So whatever our data set is, the sum of all the x's minus the mean, it's always going to be equal to 0. So we can't use just the average deviation score. So the sum is always equal to 0. Instead, we use what's called the sum of squares. And don't be confused by this term, sum of squares. Some Students confuse this and think it means that it is the sum of each x value squared. So if you took your x and then your x squared, 1, 2, 3, and took x squared, 1, 4, 9, and sum those up, and you get 14, some people would think that would be the sum of squares. No, it's, like I said, it's a bit of a misnomer. It's a bit misnamed. The full name for sum of squares is actually what's right here. The sum of the squared deviations from the mean. So the sum of the squared deviations from the mean. So I had already done it earlier when I did the one before, but what you do is instead you take each score from the mean. In this case, the mean equals 2. You take each score from the mean, 1 minus 2, negative 1, 0, and 1, and then you square them. So x minus the mean squared. So negative 1 squared is 1, 0, 1. You get this total of 2. So in this case, our sum of squares is equal to 2, because it is the sum of, added up, sum of the squared deviations from the mean. Now, why are we calculating the sum of squares? Because the sum of squares is not our measure of variability we're going to use. It is going to be a number that is too high because we actually squared everything. Because we squared everything, it's going to be values that's too extreme. Plus, because sum of squares is never negative, since you're squaring all values are going to be positive, so you sum up all positive values, you're going to get a sum of squares that's positive. Since sum of squares is always positive, you cannot tell at this point which direction it's going. You can't, but the basics it comes down to is this is a necessary step towards getting us to our end goal, calculating an average deviation score. Again, up at the top, it's impossible to calculate an average deviation score by itself. So what we do instead is get the sum of squares, and we use that as the first step towards getting an average deviation score. Here's an example of sum of squares with some pretty big numbers. So we've got this mean of 9.09090909. We've got, these are our ID variables over here. These are our x variables, ours. So each one of these is the x minus the mean. If you sum those up, you essentially get 0. There's a little bit of a rounding error, but you essentially get 0. But if you square each of the deviations, what you're doing here, and then add all of them together, you get a sum of squares of 466.91. And just like I was saying before, what does this 466.91 mean? It doesn't mean anything. It just means that the sum of squares is that. It's not a value that we can use directly to interpret the variability. Anytime you've got larger data sets, your sum of squares is going to become larger. This is just a sum of the squared deviations from the mean. It is not a value we can use to interpret yet. In the next step, we're going to get to interpretation. So now we need to calculate the variance. So now what we're going to do is take that sum of squares that we've got, that sum of squares, and we are going to divide it by our n. As I said before, as your sum of squares gets, or as your n gets larger, as your number of observations in your study gets larger, your sum of squares is going to get larger. So what we're doing when we're dividing by n is we're actually taking an average amount of squared variance. It's still squared. You still see the square here because when we did sum of squares, we squared each value. So we are getting an average amount of squared variance, or squared variability, or squared deviation, average amount of squared deviation from the mean. It's still not fully interpretable, but we do get this formula here. That is the sum of squares divided by n, and this is our variance. The symbol you see over here, sigma squared, is our symbol for variance in populations. So population variance, you'll just use S squared for sample variance. So if we take our example from the previous slide, where we had a sum of squares of 466.91, we had an n of 11, we factor that out and we get a variance of 42.45. Again, this isn't even a value yet that we can use to interpret because we still have that square in there. When we took each of the differences from the mean and squared them, we were basically inflating the value by squaring them. So this is in a sense, what this is an average squared deviation from the mean. It's an average squared deviation from the mean. So now, to put it into an interpretable form, we need to get rid of that squaring. A very easy way to do that, we just take and get the standard deviation. Standard deviation is going to be our final form of variability for the mean. And to get the standard deviation, we just take the square root of the variance. So we've got here, and you see here is our symbol, sigma for population. So the population standard deviation, S, will be our sample standard deviation. Sorry about the squeaking from the pen on the tablet. But to do this, we just take the square root of our variance. Or you could take the square root of the sum of squares divided by n, because sum of squares divided by n is the variance. Or the full formula is the square root of the sum of x minus mean squared divided by n, which is just the sum of squares divided by n. So this is the measure of variability we use with the mean. We can now use this to interpret what is going on with that data set. And I just put it here. On the previous slide, if you remember, we had a variance of 42.45. To get our standard deviation, we're going to take the square root of 42.45. Square root of 42.45 is somewhere around 6.4. So I'm going to do roughly 6.4. But what's going on here is that now we can use this value to interpret it. What this means is that the average variation around the mean is 6.4. The average difference from the mean a score is 6.4. So this is now an interpretable value. And that's why we use the standard deviation as our measure of variability with the mean. Up to this point, I've been giving you what's called definitional formulas. You guys are advanced enough, though, to be able to get these what's called computational formulas. Computational formulas are formulas that are typically easier to calculate. So a definitional formula, if you remember back, the definitional formula for sum of squares was equal to the x minus the mean squared. This is the definitional formula. What a definitional formula is it basically tells you in the formula what is going on. So sum of squares, this was sorry, I didn't put the sum symbol in there, so it's equal to the sum of x minus the mean squared. So the sum of x minus the mean. So for sum of squares, it was the sum of the squared deviations from the mean. Definitional formula, that's pretty easy. However, there's a computational formula for sum of squares over here that's actually easier to calculate. And in small data sets, you can use the definitional formula. But do you want to, if you're going through and doing 10, 15 let's say your data set has 10, 15 values, even 100 values, but you'd be using a computer program for that. But let's say you had 10, 15 values. Would you want to calculate and do each score subtracting the mean and square it? No, that is time consuming. Instead, we can use this computational formula to get the same thing, but instead we are using simpler to calculate things. Let's actually go back to our x. We had 1, 2, 3, just a very simple one. We had a mean here of 2. We did our x minus the mean squared, if you remember doing that from the previous slides, equals 2. So sum of squares equals 2 there. But there's actually another way to calculate this. We can calculate it using this formula here. Now, to do this, we need to get our sum of x. So we're going to do a sum of x here, which is 6. And we need to take and square each x value. Squaring each x value is easier to do than taking each value from the mean and squaring it. So we've got 1, 4, and 9, and we need to sum those together. So we get 14. Now we can take this formula over here. Sum of squares equals the sum of x squared minus the sum of x, that value squared divided by n. So we get our sum of x squared here, that's that 14. 14 minus our sum of x, which was 6, that value squared divided by n, which is 3. So it's equal to 14 minus 36 divided by 3 equal to 14 minus 12 equal to 2. Now, that's that same answer we got here. We get 2. It might seem like that's a bit more because the formula is a bit longer, but we already spent all the time doing this on a previous slide, and that is with only 3 values. Again, if you've got 10 values, it's way easier to square each x than it is to take each x away from the mean. So again, I leave it up to you which formula you want to use. I much prefer when doing things by hand to use computational formulas because they're quicker and easier, but the definitional formula you have for the different things that you might do where you want to know actually what's going on with the formula. So again, sum of squares, sum of squared deviations from the mean, it's actually in the formula there. Okay, real quick, just one extra thing to add to what we're talking about here, and that is variance estimate and standard deviation estimate. So one problem is when you're doing samples. So we've been talking about difference between standard is a sample and population, and I've been giving you the symbols for population, but I also gave them to you for sample real quick. One issue with the samples is that the variance is biased in samples. The variance it systematically underestimates variance. So we actually have a correction factor when we're doing samples, in that we do our sum of squares divided by our degrees of freedom. So degrees of freedom, that's something we'll go into more later. But for the most part, if we're talking about one sample, so in this case, we're looking at one sample. In one sample, the degrees of freedom is going to equal n minus 1. There are times later where we'll look at other things where degrees of freedom is different than n minus 1. But for now, because we're only dealing with one sample, degrees of freedom is n minus 1. So instead of taking our sum of squares and dividing by n, we take our sum of squares and divide by n minus 1. And to get our unbiased estimate of standard deviation, we do our sum of squares divided by n minus 1 and take the square root of that. You see these little hats on top? That's actually the mathematical term that some people use, is hat. Again, different statisticians use different things, but I just use the term hat. In a sense, what that is saying is it's the unbiased variance estimate. From here on out, we will not use the hats, but we'll still use this method of calculating variance and standard deviation for samples in order to get that unbiased. These are all the symbols that I put on other ones, except the mu here that I didn't put on for population mean. But you've got mu, sigma squared, and sigma for your population parameters, and x bar, s squared, and s for your sample statistics. These are the values you should be using. Just quick final note about variability. That is that standard deviation gives us a measure of dispersion relative to the mean, and while range gives us absolute measures of spread between extreme scores. And semi-interquartile range, again, same way. It's an absolute measure of spread between scores. So it's, again, just like with the mean, the standard deviation is sensitive to each score in the distribution, whereas the interquartile range, the semi-interquartile range, is not. It's only going to be affected by individual values that are at those quartiles. Okay, the last thing we're going to talk about, just a couple quick slides, is the shape of distributions. So we've got our normal distribution here at the top. That is, it's a bell curve. You'll sometimes see it like this. And let me erase that and try that again. You'll sometimes see it like this. Still not perfectly symmetrical, but it's supposed to be where one side is a mirror of the other side. Then you can have skewed distributions, positively skewed and negatively skewed distributions, which we'll look at in a couple slides. And then you can have uniform distributions, which is where basically all of the values are the same. So there is no, in a sense, rise or fall in the distribution. There's two important concepts that come into shape of the distribution. The first is skew. So skew is the symmetry of the distribution of scores. So we talked about skewed distributions, and that is basically how they're asymmetrical. They're not symmetrical. Whereas you also have kurtosis, which is the peakedness, how tall the distribution is. So kurtosis is almost a measure of spread in the distribution. Distributions with lower standard deviations will have higher kurtosis. Distributions with lower standard deviation or higher standard deviation, higher standard deviation will have lower kurtosis. Lower standard deviation will have higher. But that's not an absolute rule. That is a relative rule. So kurtosis is relative peakedness, as in how clustered around the central value are the values. And you can have a standard deviation that's a certain value and still have kurtosis that's a problem. We'll come back to that in just a second. Let's first look at skew. So you can have, first example is positively skewed or right skewed. And I always like to, when I'm looking at these, I teach it this way: draw a cat face, and my cat face is going to be horrible. So yeah, I told you I'm not an artist. But you've got a cat face here, and what direction does the cat's tail go? The cat's tail goes this way. That shows that it is right skewed, or it goes in the positive direction, it is positively skewed. So that is one way to remember if something's positively skewed or negatively skewed, which we'll talk about next, is which direction is the tail going, and the tail is going in the positive direction. And oh, that's even worse. I'm just a bad artist. Okay, negatively skewed, it's where the values are clustered on the lower end, the negative lower end, so it's left skewed or negatively skewed. And what it comes down to is, the big important thing is these two distributions are not symmetrical. They're asymmetrical. You cannot put a mirror in the middle. The mean is going to be pulled towards the tail in both of these distributions. It's also why we have what's called a chi-square distribution that's non-parametric, that instead of using the mean, we use, in a sense, what's equivalent to the median, because the distribution is known to be skewed. So it's a non-parametric test. The final thing to talk about is kurtosis. And kurtosis, again, is the peakedness of it. You have mesokurtic, which is basically a normal distribution, which you see here on the right. You can have leptokurtic, lepto or leap or slender, two different ways to think of it, but leptokurtic is peaked. That is, the values are clustered more in the center, and it is taller. And then finally, you have platokurtic, or plat, broad, flat, plateau, however you have to remember it. In this, the values are spread in the tails, and it has a short peak. That is all for this set of slides for this week. If you have any questions, send me an email. Thanks. Come on back.